these down. Okay. So let's go ahead and get started. We're going to pick up where we left off in our last set of notes. We had an example where we were looking at a statistics class, and we were looking at whether the students in that college statistics class could roll their tongue and they could raise one eyebrow. Hoping that sounds vaguely familiar. So we're going to revisit that example. Last time, we learned about intersections and unions. Intersections and unions. So intersection is written like an upside down U, and a union is written like a right side up U. And we know that an intersection represents an and question, and that a union represents an or question. So intersection goes with and, union goes with or. So what I want us to do is consider two new problems. If we know that a student we randomly selected can raise one eyebrow, what is the probability that they can also roll their tongue? And if we know that a randomly selected student can roll their tongue, what is the probability they can also raise one eyebrow? So I am going to give you about 90 seconds in your small groups. I want you to consider those questions. What do we think that probability calculation or that fraction would look like? Yeah? So 90 seconds. You need to talk to each other, children. And Ava and Lily could go sit together so you had somebody to talk to if you were feeling especially motivated. Do we really need that open in the middle of notes today? No. You had a work day yesterday. You had a weekend. Was me not doing this on the float during homecoming enough? Now you need me to do it in the front of the class.
Why is it like a bomb?
I don't know. I bought it because I like the pretty rainbow colors. Don't judge me. All right, so before I get out my random name caller, do we have a volunteer who can tell us what they're thinking for that first question? If we know they can raise their eyebrow, what's the probability they can roll their tongue? We're being shy this morning. Okay. Where is my name caller? Julian, what are we thinking?
I did 42 divided by 52.
So 42 over, was it 62?
Yeah.
0.67? Yeah. Can I get a thumbs up if we also got 42 out of 62? Did anybody else think 42 out of 62? And I'm getting thumbs up at the neighboring table. Thumbs up at the table over. A bunch of people flipping through there. So let's look at where 42 out of 62 came from. 42 is the both they can raise one eyebrow and they can roll their tongue. 62 is the raise one eyebrow. I'm just going to write it P raise because I don't want to fit eyebrow in there. So it looks like you guys decided the denominator of that fraction by the if we know part. And I agree. We know they have to be in that raise one eyebrow row. Good. Following that pattern, what would the next one be? Who can tell me? What would the next one be? We seem shy this morning. Jeanette, what are you thinking? That's okay. 42 over 149, which we know the 42 is P both. Where did the 149 come from? Good. That's the total from the roll their tongue column. 0.28. Good. And you'll notice the bottom of that fraction meets the if we know that they can roll their tongue. That thing that we've been underlining, the thing that's forming the bottom of our probability fraction, is known as the condition for our probability. And these probabilities that we just calculated are called conditional probabilities. So a conditional probability is a probability where instead of looking at the whole group, we're looking at a very specific subset of the group. So, in statistics terms, a conditional probability is the probability that one event happens given that another event is known to have happened. And the event we know that has happened again is called our condition. So we write this, if we want the probability that A happens given that B has happened, we would write that as P A slash B. Notice that slash is nice and vertical. And we would read that as it's written. That's the probability of event A happening given that we know B has happened. And that condition is the thing that comes after the slash. The thing that comes after the slash is the thing we know has happened. The thing that comes after the slash is the bottom of our probability fraction. That's the group we're limited to. And then I want to know how many A's I have in B. So let's do an example. Yeah. It says the Titanic struck an iceberg, sank on its very first voyage across the Atlantic Ocean in 1912. Some passengers got off the ship safely in lifeboats, but many others did not and died. The two-way table gives information about the adult passengers who survived and who died by class of travel. Suppose we randomly select one adult passenger from the Titanic. Define events F as first class, S as survived, T as third class. Find and interpret the following. PT given S and PS given not F. FC. So let's go through the pattern that we just used. So we know the pattern for PA given B is P both divided by the condition PB. We also know we can do it with frequencies, which is what we did in the last one. The frequency of both divided by the frequency of B. So for the probability that they were third class, given that we know they survived. So let's start with the numerator of that fraction. Who can tell me the numerator of that fraction? Where is the third class and survived? Birdie, where's my third class and survived? 151, good. And then my condition is survived. Mario, how many people survived? 442, yeah. We grab a calculator. And we round to 3 decimal places, and I get 0.342. Assuming I know how to round this morning. Yay. Thank you for the thumbs up. Good. Very good. Same principle on the next one. So I want the probability that they survived given that they were not first class. F not C. So let's color code. I need to know where all of the people who survived and were not first class are. Where is that in my table? Better question, is that one box or more than one box? More than one box, because not first class is second class or third class. So that's 2 boxes. I want survived, so I'm in the top row, and then second and third class. And I see some nodding, so we want to add those 2 together. 245. Thank you, Jeanette. My brain's a little slow today. And then the bottom is the count for the condition, which is not first class. Where are those boxes in my table? Bottom totals, good. I want those 2. So 888. Let me grab our calculator. 245 divided by 888 is 276, rounded. Good. Good. What we're learning, conditional probabilities, instead of looking at the whole, we're now looking at one specific column or one specific row. We're narrowing down the group we're considering. Good. Good. Questions on the first example? No. Okay. So, formula for probability, when it's conditional, PA given B is PA and B over PB. Probability of both over probability of the condition. And on your equation sheet, it won't be written like that on test day, because instead of writing PA and B, how will Ray write that? Intersection, very good. Intersection, upside down U. Very good. And it works with probabilities. It also works with frequencies directly from a two-way table. Good. Let's try another one. Next one says, in a sample of U.S. high school seniors who responded to the census at school survey, 87% said they plan to attend college. 42 said they felt a lot of pressure because of schoolwork, and 37% said both of these were true. If a randomly selected student from this sample feels a lot of pressure because of schoolwork, what is the probability that they plan to attend college? So we're going to write our probability using probability notation. We're going to set up our fraction. We're going to calculate the proportion or the decimal, yeah? So first, I need to write my probability notation. Probability of what? It's the very last part of the question. Mario, what's the last part of the question say? Good. So this is attend college. And what do we know about this student? Feel pressure. Very good. Given that we know they feel pressure. And we know what that fraction looks like. It should be the probability of both over the probability that they feel pressure. If I could spell today. Both divided by condition. So we go to the word problem. Ava, what's the probability that they feel both? Both attend college and feel pressure. Very good, 37, so 0.37. We do math with these numbers in decimal form, not in percent form. Good. And Carolina, what is the probability this student feels pressure? 42%, 0.42. Good. So 0.37 divided by 0.42, and we get 0.881 rounded. You see some line. So 88% of students who feel pressure are planning to attend college. Good. Okay. Questions on conditional probability? No. All right. Next idea related to this idea of conditional probabilities. Two events are called independent if the probability of one is not affected by knowing the other happened. Happened, not happened. So examples of independent events. Knowing that you're taking AP statistics tells me nothing about the type of shoes you're wearing in the morning. Those two things are completely independent. The probability that you are in AP statistics is completely independent of the probability you happen to be wearing tennis shoes this morning. There's no connection in reality. I don't expect knowing that you wore tennis shoes is going to tell me anything about whether you're taking AP stats. Those would be independent events. If two events are independent, meaning knowing that I did A tells me nothing about whether or not I did B, I expect that the probability of A given B should just be the probability of A, because A doesn't depend on B. And the reverse is true. The probability of B given A should just be the probability of B. Okay, so someone with a nice loud voice want to read out our next example? Thank you, Halo.
Is there a relationship between subject thought and handedness? To find out, researchers chose an SRS of 100 teachers at an education conference. The two-way table summarizes the relationship between the subject thought and the dominant hand of each teacher. Suppose we choose one of the teachers in the sample at random. Are the events teaches math and left-handed independent? Justify your answer.
Very good. Thank you, Halo. So, last statement says, are the events teaches math and left-handedness independent? I know if they're independent, P teaches math given that they are left-handed should just be P teaches math. Yeah? P left-handed given that they teach math should just be P left-handed. So we're going to check these relationships and see if those statements are true for this table. If they are true, the events are independent. If they're not true, the events are dependent. So let's go ahead and calculate these probabilities. So we're going to calculate P, and let's call teaches math A and left-handedness B for ease here. So I want PA, I want PB, and then I want PA given B and PB given A. So let's start with PA. What is the probability that a teacher at this conference teaches math? Out of 100, so 0.46. Perfect. We like things out of 100. They're easy to calculate. All right, what's the probability that they are left-handed? 0.1, 10 out of 100. 0.1. Yeah, good. And let me make some more space here. So now we do the conditionals. We're going to have to set up fractions for these before we get the decimals. So for PA given B, I know that's P both over PB, or the count for both over the count for B. So how many people both teach math and are left-handed? Where is that box in the table? 7. Left-handed math nerds. Good. So I know the top of both of these fractions is going to be 7. It's both and both. For the first, PA given B, I want the count for just B, which is just left-handed, which is where? 10. 7 out of 10, which is 0.7. I don't even have to do the next one. Are these events independent? No, because PA and PA given B are wildly different. We'll do the next one, but we already know these guys are not independent. For P, B given A, it's the count for both over the count for A. How many math teachers? 46, so 7 out of 46. We need a calculator for that. And I get 0.152. Slightly less off than the first one, but still not equal to PB by itself. So these two things are not equal. These two things are not equal. Therefore, we know that these events are not independent. Knowing one does affect the probability of the other. An important note before we continue. Just because there is a connection between left-handedness and teaches math for this sample of 100 math teachers, or teachers at this conference, does that mean that there is a connection between teaches math and left-handedness for all teachers in the nation? No. So we see a connection here for this sample. We don't know that this sample represents the whole population of US teachers. So we have to be very careful when we talk about independence for samples that we don't interpret that as statements about a population. When we get to Unit 8, we're going to learn how to perform tests about whether that sample represents a big enough difference that there is also a difference in the population, or whether it represents a strong enough relationship that we know there's also a relationship in the population. But that's second semester. So for now, keep in mind, this only tells us about the sample that we collected. No inference yet. Good. Okay. So next is our second probability rule. Last week we learned about the addition rule for or questions. Now we have the multiplication rule, which is for and questions. So if I have P, A, and B, the probability that the events occur together, and tells me to multiply. So that would be PA times PB given A. If the events are independent, this is just PA times PB. But if they are dependent, I have to use a conditional here. P first times P second, knowing that first happened. Again, on your equation sheet, they're not going to write it this way. What are they going to write? Very good. PA upside down UB. P intersect B. A intersect B. Good. Good. So we know or means add, and then if they're not mutually exclusive, subtract the overlap. And means multiply, make sure that second probability is conditional. Let's try some so we know what that looks like. All right, first example says a carpenter is replacing a hinge on a cabinet door, needs to pull out 3 identical number 10 screws from a box of screws. There are 5 number 8 screws and 15 number 10 screws in the box. If the carpenter reaches into the box and pulls out 3 screws at random, what is the probability all 3 screws are number 10 screws? So, what is this asking? In statistics language, this is asking us the probability that I draw a number 10 screw, and then I draw another number 10 screw, and then I draw another number 10 screw. So I'm drawing 3 screws, one after the other after the other. I want them all to be number 10. Yeah. And I know that should be probability that I draw a number 10 times probability I draw a number 10 given the first was a number 10 times probability that I get a number 10 given the first 2 were number 10s. And that sounds complicated. It's not as messy as it sounds. So we're going to think through this logically. I know I'm multiplying probability times probability times probability. Fraction times fraction times fraction. Yeah. And we're just going to set up each fraction using what we know about the system. First fraction, have not touched any of the screws in the drawer. How many screws are in the drawer? 20, 5 and 15. Good. So 20 screws in the drawer. Out of those 20, how many are number 10 screws? 15. So I have a 15 and 20 chance of drawing a number 10 screw out of that drawer if I'm not looking and I just like stick my hand in and grab. I have now taken a number 10 screw out of the drawer and slapped it on the table. How many screws are left in the drawer? 19. Of those 19, how many are left that are 10s? 14. Yeah. Good. Second draw, I've taken another number 10 out of the drawer, slapped it on the table. How many screws are left? 18. Of those 18, how many are number 10s? 13. Yeah. Remember that when you multiply fractions, you multiply across the top, you multiply across the bottom. Your calculator is stupid. So 15 times 14 times 13 divided by 20 times 19 times 18. And let's see what that gives us. 0.378. Can I get a confirmation? 0. What was it? 378? Did I do this wrong? 15 times 14 times 13 over 20 times 19 times 18. I got 0.399. Somebody else try it. What are we getting? What did you get, Ariana? 399? 399122, yeah. So 15 times 14 times 13, parentheses, divide, and then parentheses, denominator. Yeah. Whoops, I didn't mean to do that in red. So there's about a 40% chance that if I draw 1 screw at a time, 3 screws in a row, all 3 would be 10s. Less than half, not great. Good. I am going to give you a couple of seconds, 90 for good measure. I want you to try the second example. A bag contains 5 red marbles, 8 yellow marbles. Suppose you randomly select 2 marbles. What is the probability they're both red? Give you about 90 seconds. Good. I see us writing probability notation. Good. Oh, I need to fix attendance. Jackie, did you have a pass? Thank you. Okay, let's see who we can pick on. Ariana, how do we tackle this question? What should we do? So red intersect red, okay? Five over 13. Good. And what did you get when you did that? 128. Can I get a thumbs up if we also got 0.128? Very good. Very good. For both of these problems, we drew a screw out of the drawer. We kept it out of the drawer. There were less screws in the drawer for the second draw. For the marbles in the bag, we took a marble out of the bag. We kept it. Fewer marbles in the bag. That process is called drawing without replacement. Another example of drawing without replacement. When you play card games and you set up your initial hand, you draw a card from the deck, you keep it for your hand. There's now fewer cards for the next draw. Yeah. When we draw with replacement, we automatically have conditional probabilities as our second, our third, our fourth, because we're changing the deck with each draw, changing the contents of the drawer with each draw. There is another process related to that called with replacement, meaning I take it out, I write down on a piece of paper what it is I selected, and then I put it back in and I stir, so it's random for my second. When it's with replacement, the bag of marbles looks the same for the first and second draw. And in that case, it's just probability, probability, probability. There's no condition because it's the same drawer, the same bag of marbles for each draw. Good. Okay. Questions for our multiplication rule? And shaking our head. No, not too bad, right? Or means add, and means multiplication. We can do this. Okay. So now, for another tool, we talked about Venn diagrams last week. Great way to picture how two events relate in a sample space. A tree diagram is another type of picture that helps us figure out what a sample space looks like when we're doing multiple events in sequence. One draw from a deck, second draw from a deck, third draw from a deck. So it shows the sample space for a random process involving multiple stages. When we build tree diagrams, typically for each branch in the tree, we also write the probability of that event happening as we go, because if I follow a branch, I'm just multiplying the probabilities for each branch to get the probability of the total outcome. So this isn't just going to help us figure out what our sample space looks like. It's going to help us calculate these general multiplication rule problems. So we're going to do some examples so you can see how to build one, how to use them to find probabilities. Okay, someone who hasn't read yet want to read that example for us? Thank you, Leo.
The use of e-cigarettes vaping has become a public health concern in the U.S. Despite the dangers of vaping, recent data from the National Health Interview Survey suggests that 26% of adults aged 18 to 24, 21% of adults aged 25 to 44, 11% of adults aged 45 to 64, and 5% of adults aged 65 and older are vaping. According to the U.S. Census Bureau, 9% of U.S. adults are aged 18 to 24, 36% are aged 25 to 44, 33% are aged 45 to 64, and
Very good. Thank you, Leo. So they ask us to do two things with that big paragraph of information. The first is let's organize it in a tree diagram to model this process of randomly selecting adults and recording which age group and whether they vape. And then we're going to use that probability to find use that tree, to find the probability that the selected adult vapes. So when we're recording, what's the first thing we record about this randomly selected US adult? We record age group, right? Which age group, and then whether the person vapes. So I'm following it in the order it was given. So my first branch in the tree is going to be by age group. How many age groups did they give us? 4? 4. So my first branch in the tree should have 4 branches. And I can't draw, so bear with me here. And then I'm going to record 2 things on those branches. The nodes here at the end are going to be the age groups. So first age group was what? 18 to 24 years old. Next one was 25 to 44. Okay, next one was 45 to 64. And then 65 and older, yeah? Okay. And then I'm going to record for each of those branches what proportion of US adults fall in that category. So that was the second to last sentence. So US Census Bureau, 9% are 18 to 24. So that's 0.09 in decimal form. 36 are 25 to 44, 0.36. 33 are 45 to 64, 0.33. And then 22 are 65 and older, 0.22. Writing sideways is hard. Okay, next thing I record about these people. I've recorded their age group. What else am I recording? Whether or not they vape. So for each of those age groups, there's then a branch. Some people vape, some people do not. So vape, not vape, vape, not vape, vape, not vape, vape, not vape. On the AP exam, if you use shortcuts like I'm doing here, and V and NV, somewhere on the paper I need to write V stands for vape, NV stands for not vape. They're going to expect you to define any shortcuts. You can do that off to the side if you want. And then we go through the process of labeling those branches. So of the 18 to 24s, how many vape? What percentage vape? 26%? Is it 21%? Suggest 26 of adults age, so it is 26. Okay, I can read, yay. So this is 0.26. If 26% vape, what percent do not vape? 74, very good, 0.74. And then we're gonna follow that process. So next age group, 21% vape. So 0.21, 0.79. Next age group was 11, so 0.11, 0.89. And then last one was 5%. So 0.05, 0.95. The nice thing about this tree diagram is now that it's set up, if I want the probability that a randomly selected 18 to 24-year-old vapes, I just follow that branch and multiply the numbers, 0.09 times 0.26. I want the probability that a 45 to 64-year-old does not vape. I follow the 45 to 64 not vape, 0.33 times 0.89. I multiply down the branches that correspond with the outcome I'm interested in, which is nice. So what I would like you to do, take a second for each node in that table, and I see 8 total outcomes. 1, 2, 3, 4, 5, 6, 7, 8. The tree has 8 outcomes. Find the probability. Multiply each branch. I'll give you about 90 seconds. This is a quick calculator math, right? Plug and chug. 0.09 times 0.26 all the way down the tree. Please do this. Double check that I'm doing it correctly. So those are the numbers I got when I multiplied down each branch. And while you are copying that down, a couple patterns to notice about the table. We'll finish this example when I see you tomorrow. At each stage of the process, the probabilities along the branches should add to what? 1. So all 4 age groups should add to 1, because that's everybody. For each age group, vape plus not vape should add to 1, because that's everybody in that age group. If I add all of these probabilities along that last branch of the tree, should add to 1. Yeah, because that's everybody in the tree. Out of those outcomes, how many of them represent people who vape? Should be 4, right? 1 from each branch, because that's the question. Randomly selected adult vapes. Vape, 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 vape. Before you leave, what are we going to do with those probabilities? Add. Very good. We'll pick up where we left off today, tomorrow. Please bring these notes with you. Tomorrow we're going to do this. We're going to take a short quiz. Counts as homework, right? Just practice problems. And then we'll start 4D. If you have questions, send me an email or catch me tomorrow morning. I do have a Schools Like Council meeting today after school. I will be available tomorrow after school.